So we are definitely getting both in this case. All right, so I'm just going to read the instructions first, just so that you guys know what I was expecting last semester. I would expect I would be doing about the same thing this semester, but definitely not going to be the same code or the same program. All right, so it starts with the date and also the start time. So obviously that's also going to change for you guys because you are not in the same um, section as last semester. Let's see, get rid of that. There we go. And this is an individual exam, no collaboration, and so on. That's a typical thing. Your exam is also going to be on paper, so I'll be printing this out, and you can bring additional sheets of paper if you want. You'll be writing on basically the exam itself. So that is also a big difference between the one from last semester because that was online, and the one that you're going to take, which is here in person and also on paper. You can use any material, but not live interaction with another person. So because this is an in-person exam, so you can only use things that are on a piece of paper. No electronics during the exam. Um, so all of these tools are no longer available, just because we are taking the exam on paper. So some of this would need to be changed. All right. So getting to the actual content of the exam, it starts with C code. So this is the actual C code um, that I want to implement in assembly. So we'll go ahead and start with the C code because I do want to make sure that we understand the C code. This also relates to your homework assignment, the one that I have postponed the due date to Wednesday. So here's a structure definition. A struct node has a pnext as a member and also a value as a member. One is a pointer, which means it takes up 1 byte. The other one is definitely 1 byte because it's an unsigned 8-bit integer. And then we have 3 global variables in this case. So the way you can have global variables initialized is to use a syntax like this. Do we have any questions about the syntax of a initialized global variables that are of a structure type? And lines 36 to line 38 is basically how we can have these global variables. Yep.
So they're just initialized to like the pointer next is
It's
the
null.
p next is 0 or no, and then the value is 4, 2, and 5.
Yep.
Okay.
But there are 3 structures.
Right.
Okay, there are 3 structures, N3, N2, and N1 respectively. Yep. Okay, that's a good question. Anything else? Are there any additional questions about these 3 lines of code from line 36 to line 38? Okay. All right, so line 40 to line 54 is the actual subroutine to be implemented. So in this case, here we have a function f that returns a pointer to a pointer of a struct node type. And then as parameters, it has a pointer to a pointer of a struct node as the first parameter, ppn. ppn stands for a pointer to a node. Okay, that's why it's called ppn. And then the second parameter is pn because it is just a pointer to a node. Inside the subroutine, we have a local variable, which is result. Result also is a pointer to a struct node. Okay, so I'm going to pause here and make sure that everybody understand what is a pointer to a pointer, that sort of concept. So are we comfortable with that concept? So we have structure, we have a pointer to the structure, then we have a pointer to that structure. Are we okay with that? It's basically, as you track down what it points to, what do you find at the location that the pointer is pointing to? So a pointer to a struct node means if you follow that pointer, you will find a pointer to a struct node. If you follow a pointer to a struct node, after you follow that address, you find the beginning of a struct node. All right. So the code here on line 43 is checking whether what ppn points to is null or not. In other words, we want to dereference ppn just once and then find out whether what it points to is a null value or not. If it is null, then this portion is going to be true, because when something is null and you negate it, it becomes true. Are we doing okay so far with the left-hand side of the logical OR?
Say it again. So you're checking that if it's null or not, right?
You're checking whether it is 0 or not, basically. And if it is 0, that makes it true. In other words, this notation here, okay, let me just gonna copy and paste so this way I don't destroy the original one. This notation is really truly saying the same thing as that. It just wants to see if ppn is pointing to a null value. Is that okay? Because the null value is also known as false. So these two basically do the same thing. It's checking, not false is the same thing as that thing is a 0. And then the right-hand side of the OR is checking whether the value member of the structure that is pointed to by the pointer that in return is pointed to by ppn is greater than the member value of the structure the pn is pointing to. Is that okay? So I know it looks kind of confusing, but when you are looking at the code or when you're implementing something like this, you basically just have to do it one step at a time. And that's why it is super important to understand what is in a register as you write your code in assembly. All right? So I want to pause a little bit just to see if there are any questions regarding line 43, which is equivalent to line 44.
So is the value of what the pointer to a pointer is pointing to is bigger than the pointer itself?
No. So okay, so the greater than has a left-hand side and a right-hand side.
Yeah.
Which side you want to deal with first doesn't really matter,
Mhm.
because it's just you want to confirm it is greater than. The left-hand side is referring to a member called value of a structure, but that structure is pointed to by the pointer that in return is pointed to by ppn.
Okay.
So this is where a picture can be useful. If you use, this is where paper-based exam has a slight advantage, because you can actually draw stuff, right? So let me see if I can draw this. Okay, give me a second to set up my the tool for demonstrating drawings. That would be it'll be fine. All right. So this is the virtual whiteboard, and let me go find the original, and also have to change the stylus scaling stuff. Just give me a second. There we go. Okay, got the stylus out. And where's my Zerno? Right here. There we go. Okay. All right, so all right, so we'll take a look at memory space. So let's just say that this is memory space, and this is the call frame of this particular function. So what is on the call frame? We have all the parameters, we have the return address, and then we have all the local variables. They're all a part of the call frame. So if this direction is pointing to high memory address and this direction is pointing to low memory address, then the call frame itself is going to have the two parameters. The first parameter is ppn. So I'm just going to say this is ppn. This is pn, followed by return address, and then followed by the local variable. So let me check how I called the local variable. I think it's a pretty simple name, but I cannot remember. Result. Okay, so I was right. It is a very simple name that I used. So here is result. Oh, okay, you cannot see that because I forgot to put that back on like that. Okay. So when you draw a picture, you want to say, okay, but what is PPN? PPN is a pointer to a pointer. So if this is the top of the stack, it typically means somewhere else is a pointer. So PPN. Okay, I probably want to copy this to a lower portion. And let me see, what tool do I need to use here? Select rectangle. There we go. And it's moving everything but that one little thing. Okay, so that's fine. I can manage that. We'll just go ahead and erase this one, and then we draw that here. Okay. So this is a call frame. There we go. And then somewhere else in memory, okay, is a pointer. And then somewhere else in memory, which I don't even know where it is the actual structure. So this is the actual structure. It is of the type struct node. And what happens is ppn points to this location, and then this location in return points to the base of a structure. So ppn is a pointer to a structure. And then the structure itself has two members. The first member, if I remember correctly, is pnext. So pnext is the first member of the structure. And then the second one, if I remember correctly, I just called it value. So is that okay so far? All right. So what about Pn then? Well, what about Pn? Well, Pn is a pointer to a struct node. So that means, if I have another structure somewhere, okay, so let's just say that this is another structure. So this is another struct node. Then Pn does not go through an intermediate pointer. It itself points to the base of the other structure. Is that okay? So with all of this stuff here, if you're inside the subroutine F, which is what we want to implement, the stack pointer would be pointing here after we set up for the local variables. So yes, we have a lot of pointers, and this is why CISP360 is a super important prerequisite for this class, because your CISP360 talks about pointers and also structures. So are we still doing okay so far with this picture? Okay. Now this is also something that you might want to do with your homework assignment, is to get an idea of okay, what is a pointer? What is it? Where is it pointing to, or what it is pointing to, and so on. The exam question is a little bit, just a tiny bit, more complex, that we have a pointer to a pointer instead of just a pointer. Are we good so far with this picture? All right. So if we are okay with this picture, then we will continue to talk about the code. So we move on to this part here, the left hand. So when you look at something like this, you just separate the right hand side from the left hand side. The right hand side is just whatever ppn is pointing to, and what ppn is pointing to is a pointer itself. So we are basically just looking at the address of something as the right hand side. The left-hand side is the member pnext of the structure the Pn is pointing to. On the next line, your Pn itself is really just the parameter itself, not even what it points to. And then on the left-hand side, we have whatever ppn is pointing to. And then the last line is a pretty straightforward copy. We just look at the parameter ppn, and then we copy that to the local variable result. So that's what the non-recursive version is going to do, which is from line 46 to line 48. And then the recursive version, which is on line 52, is pushing two arguments on the stack. The first argument is Pn itself. We just take the parameter Pn and push that on the stack to perform the recursive call. The second one, the first parameter, the first argument, looks complicated, but it's actually less complicated than it looks like, because we are taking the address of the member pnext of a structure that is pointed to by a pointer, and the pointer itself is pointed to by ppn. Okay, So if we refer back to the picture, okay, let's go back to the picture that I showed you guys earlier. I think it's, nope, not that. Where is that? Nope, nope. Huh. Right there. There we go. So what we're looking for in this case is we follow ppn. It points to a pointer. That pointer in return points to a structure, and then within that structure, let me go back to the code because I can't remember which part of the code I'm changing. So the code is changing p next. All right. So let's go back. Well, it's using p next. So it's basically trying to figure out the address of p next, and the address of p next as a member of this particular structure becomes the argument, the first argument that I need to push. Is that okay? So there are only a few main basic concepts, okay? The main basic concepts in this case, the first one is structure. What is a structure? Well, a structure has members. Each member is identifiable by its name, right? And all the members are ordered as the way they are defined inside the structure. So that's the basic concept of a structure. In the assembly code, we use a label to to basically record the number of bytes from the beginning of a structure to each of its members. So those are the labels that we define, in place of a structure definition. So that's the first concept. What is a structure? What does it look like? And how it is represented in assembly code. The second concept is a pointer. Okay, what is a pointer? Well, a pointer is basically it contains an address. Well, it's an address of what? Well, it depends on the type of the pointer. If you have a pointer to a struct node, that means if you follow that address, you will find the first byte of a structure. If it's a pointer to a pointer, what do you get when you follow that pointer? A pointer. Okay, so you're basically just decreasing the number of referencing by one when you dereference a pointer.
So, Professor,
So yeah.
just to clarify, the pointer to a pointer,
Mhm.
it doesn't point to the thing the pointer is pointing to. It points to the pointer itself.
Yes. So in this case, the ppn is a pointer to a pointer. So you can see how it points to a location in memory.
Right.
But the content at that location is by itself also a pointer.
Pointer.
And that pointer in return points to the beginning of a struct node. So that has to do with the type of the pointer.
So you would have to dereference twice, essentially.
Once you get to the pointer, you have to dereference twice. Yes.
To get the value.
To get to
the
member, of the
right.
structure.
Okay. Not the value. Okay. Gotcha. Whatever.
Yep.
Okay.
So when we actually write the code, we need this picture to figure out, okay, at this point, where are we with this particular register? Because that is something that you need to track in your head. Now, you can use a picture to help you in the exam and also your homework assignment. And for some people, they don't like pictures, and they can just use comment to identify which register has what at a particular time. But either way, okay, it is crucial to understand what is in a register at any time of the assembly code. Are we doing okay so far with this? All right. Okay. Um, so let me continue, and then returns result. Main doesn't really do a whole lot. Okay, so this is what main does. So what main does is it has its own local variable called pnext. It is a pointer. That pointer is initialized to 0. And then we have three calls to function f. We are using the address of n1 to pass as the second argument, and then we're using the address of p first to pass as the first argument. So we call it the first time, the second time we use n2 instead of n1, and then the third time we use n3 instead of n2. So these three calls would be identical in terms of what they need to do, but in terms of the implementation, well, I can play tricks, right? I can use alternative ways to do the same thing. And that's the C code. So the assembly code is trying to do exactly the same thing, but it's faulty. Now, how do we know it's faulty? Because I artificially introduce the faults. So we know for sure it's not going to get the job done correctly. So the question is, how is it wrong? So your job is to identify where it is wrong and how to fix it. So you have to propose, you have to first identify this line is wrong or something is missing here, and then you have to tell me how to fix that line, what to insert, or this line is extra, it is not needed, then you have to tell me that that line needs to be deleted. So are we okay so far? Understanding the source code in C and also understanding what your task is in the final exam, well, at least for spring 2022. All right. So it helps to be able to look at both at the same time. So that means, I'm going to use paper clips again for this exam. So this way you can just take off the paper clip. You can just kind of, lay out, all the pages. So this way you can cross-reference the assembly code with the C code without having to flip the pages and whatnot. I'll double check. I would try to make sure that I do not print on double-sided. So this way you don't have to keep flipping back and forth to find out where's this line going and so on. All right, so at this point I'm going to cheat a little bit because I do want to turn on the split mode of VI, so this way I can focus on the C code on one side and then I can look at the assembly code on the other side. So this is the beginning of the C code, and then in terms of the assembly code, after a bunch of description, this is the beginning of the assembly code. All right, so we start with a no op, no big surprises there, okay, because I do want to run this code inside the CLI. And then we get to line 100 and go like, what exactly is that doing? It is doing an LDI-A and then the dot 8 plus, and what we do with the register A is right here, okay, so we are doing something and we do initialize the stack pointer here, and it got decremented. So in this case, I'm treating main as a regular subroutine. This is the code that calls the main as a subroutine. So what are we loading into register A on line 100? In other words, what are we pushing on the stack? Well, let's try to figure out. What is dot 8 plus? What does it mean? It's a postfix notation, so it really just means dot plus 8, okay? So the question is, what does dot represent? What is the dot representing in the context like this? Yep.
Yeah. Isn't it making space? It's making 8 bytes worth of space.
Mm, I guess that's one way to look at it, but I'm asking specifically what is the dot representing?
It's the address where we are right now, right?
Yes, so that is correct. So the dot is representing the address of the LDI instruction. LDI instruction takes 2 bytes. So we have bytes offset 0, offset 1, offset 2, offset 3, offset 4, 5, 6, 7. This is offset 8. In other words, what I'm loading into register A is the address of the halt instruction. It's basically where main is supposed to be turned to.
So the register doesn't take up any space.
Hmm?
The register itself, that the LDI command takes up 1 byte, but the A doesn't take up.
The A does not.
Okay.
So LDI-A, okay, to specify A is receiving the constant, that becomes the XX part of the opcode.
Okay.
So that's why it's not taking up an entire byte, it's taking up 2 bits of the entire byte of the LDI pattern of opcodes.
So the dot is where it's the address where the LDI is.
Yes, the dot is representing the address of the instruction of that same line. All right, so that means this is all we are doing is to push the return address, which is the halt instruction, on the stack, and then we do a JMPI to main. So the main in this case is just a regular subroutine. It got called, and as a result, it has to return. Are we good so far? All right. So now we want to check out main. So when we get to main, so at this point you have a choice of how you want to proceed with this code. You can go ahead and read the code from line 1, just do it sequentially. I typically do it using a structure, so that's up to you guys to determine how you want to do this. All right, so once we get to main, We know that main in this case is a regular subroutine. So what I'll be looking for would be code to allocate the local variable and also the code to return to the caller. Does that make sense? And I would do that first. Okay. In other words, the way I check whether a program is correct or not follows the same order that I typically use to write the program, to begin with. So I would do it structurally. So I would look at the way I define the labels and the way I allocate the space, and just to make sure that all that stuff is correct. So main has one single local variable, which is first, p first. So p first is okay. So let's go back and check on the C code. So this is the C code. When we get to main, we can see that line 58, 59. Sorry, line 59 is the only local variable of main, which is p first, and is a pointer. So when we look at the assembly code, this looks right. Okay, after the allocation, p first being at the offset of 0 from where the stack pointer points to. Yep, that makes sense. Okay, because this is the only local variable that we have, which also means it's going to be the last one. So when we compute the local variable size, which is in number of bytes, we would use main underscore p first, which is the offset to find the first local variable, plus the size of the local variable. So I want to ask you now, are we allocating this correctly? In other words, how many bytes should I allocate for p first as a local variable? How big is a pointer in TTP?
1 byte.
It's supposed to be 1 byte, okay? But when you look at line 228, how many bytes am I allocating? I'm allocating the same number of bytes as what a struct node would require. That would be incorrect. Okay, so let me just pause here and make sure that everybody understand why there is a problem on line 228.
I guess I'm just trying to find where node size was. The label was.
Oh, node size?
Yeah,
Node size is, okay, so let me put a marker here and then we can look for node size and where it is initialized. That's
Okay.
how it's defined. So this is how we define the structure in assembly code, is we look at the first member and we say it is at an offset of 0 from the beginning of the structured node, of a struct node. And then we look at the next member, which is value. It is at an offset based on the previous one plus the size of the previous one. So node underscore value is literally just 1, okay? And then we look at node size, which is needed whenever we need to actually allocate that space. It is node value, which is 1 to begin with, 1 plus, so that makes node size basically 2. Is that okay? So once we understand node size is 2, we go back to the line that we were looking at earlier, and we look at this and go like, I think we're allocating 1 byte too many. Because a pointer only has 1 byte, the structure itself has 2 bytes. So that would be wrong. Okay? So that means I need to change this line. So the way I can do this is I can say change this so that we have
Could you say main underscore p first plus 1?
yep. So get rid of node size and just make it a 1. And the reason is because a pointer only takes 1 byte. All right. So that's that. And I need to go find my mouse pointer. There we go. All right. So this is the first problem that we located and we fixed it. So now that I know the labels are right, we have just figured out the right number of bytes for the local variables. The next thing I would check, structurally speaking, is to make sure that I allocate and deallocate the bytes for the local variables correctly. So I look for the code to allocate, which is on line 231 to line 232. Does that look right to you? It does not look right because how should we change this? We need to subtract because when the stack pointer is moving down, we are allocating. When the stack pointer is moving up, we are deallocating. So this is actually deallocating before we even had the chance to allocate. So that would not be right. So that means I'm gonna um, copy and paste. I can just I mean, you don't have to do this because you're writing it on the paper, so you can just kind of cross out the add, and just write down your sub, or you can cross out the entire line and then rewrite the entire line. So either way is fine. As long as I can see what you're changing, that would be fine. Okay, so this is the first change. So I'm also checking the program in a structured way, which means I'm going to go all the way to the end of main and make sure that I am deallocating and then return at the end. So I'm looking for the end of main, and this is the end of main. All right, so when I look at the end of main, this is the last call to F. These two are to deallocate the arguments, and then this is the end of main. So the end of main, according to the C code, is return 0. So moving 0 into register A is correct. But I'm missing quite a few pieces here, am I not? Because first of all, I'm missing the piece of deallocating for the local variables, and I'm also missing the piece where I need to go back to the caller. So that means, right here, I need to first to do the deallocation. So that's done by, so I'm just going to say added the following. LDIA with main underscore LVS. This time add is correct, okay, because we want to deallocate. And we also need the usual code for returning to the caller, which is LDB underscore D, in parentheses D, increment D, and then JMP to B. So, and I can even comment here what these are for. So this is for 2 lines to deallocate local variables. And then this code is for return to the caller. There we go. So I have now checked the entry point and also the export of main. It is now to go in and actually check the implementation of main to make sure that we got all those right too. All right. So I think in this particular exam, I was being very kind and also include the C code, followed by the actual implementation of the C code. So this way, it's a little bit easier for you guys to make an association between the C code and the assembly code. So whatever follows, this line on line, starting with line 235, will be the implementation of P first equals to next. All right. So as I said, you need to know what is in a register at all time. So after line 235, we have the offset to find P first as a local variable from where the stack point is pointing to. So it's just an offset at this point. Once I add register D or the stack pointer to register A on line 236, register A now has the address of P first. And then we load 0 into register B, and then we store B into wherever register A, which is the address of P first, is pointing to. That looks right to me. Okay, it looks like it is doing what line 60 in C is supposed to be doing. So I think these 4 lines are okay. And now we move on to line 239, which is supposed to implement. Which is supposed to implement the first call to F using the address of N1 as the second argument and using the address of P first as the first argument. So this line is commented, line 241 is commented, so there's no need to worry about it because you can just pretend that it's not here. So the question is, if you look at line 240, line 242, and line 243, is that accomplishing pushing the address of N1 on the stack? N1, by the way, is a global variable. It is not a local variable. First of all, why would it make a difference? Where do you think global variables live?
In the stack.
They are not on the stack. So global variables are not on the stack, which means their addresses would not be relative to the stack pointer. So the label itself is the address of the struct node. Okay, so register A on line 240, that actually gets, register A gets the address of N1 already because a global variable is not living on the stack. So the label itself is telling us the address of that node. So line 242, decrement the stack pointer. Line 243, storing register A to where the stack pointer points to. That's actually valid. Okay, we just pushed the address of M1 on the stack. So that's all good. And then we move on to line 244, which is loading A with main P first 1 plus. So the question is, what is that 1 plus doing here? Well, the 1 plus is needed because we already have the second argument pushed at this point. P first is a local variable, as you can see in the C code, which means its address is relative to where the stack pointer points to. But P first as a label is the offset of right after we did all the allocation. The stack pointer has now changed by 1 byte because of line 242. So that means the actual offset from where the stack pointer points to P first is now 1 byte more than what the label is suggesting. And that's why we have to add an extra 1 to the label P first in order to get to the offset of P first relative to where the stack pointer points to. Is that okay so far? So it would be helpful to maintain a picture of what is on the stack and also how the um, labels are defined. So let me switch to the picture. So here's the picture. So what we have at this point, okay, so I need to use a new page. Or maybe just here is fine. All right, so what we have here is the stack frame of main. So this is main, this is the absolute limit of the stack here. We have the return address already using this location. This is the return address, so the main can return, okay? And then in main, this location is used for the local variable P first. And as a label, P first is defined to be 0. All right? So normally, right after the allocation of the local variable, this is where the stack point is pointing to. After the subtraction of main underscore LVR from the stack pointer, that's where the stack pointer is pointing to. The stack pointer is pointing right at the local variable itself. Is that okay? And the label P first or main P first is defined to be 0 because it is at the displacement or offset of 0 from where the stack pointer points to, right after the allocation. Are we still doing okay so far with this? But what we just did with the program is we just pushed the address of N1 on the stack. So when we push, that means the stack pointer is now pointing here. Is that okay? So in order to get back to the address of P first, I cannot just say, oh, it is right at where the stack pointer is pointing to, because the stack pointer is now pointing to 1 byte below where it used to be pointing to. So that's why I need to look at the label P first and say, that would get us close, but we need to add 1 to that label in order to compensate for the address of N1 being pushed already at this point. Yep.
It's a way to like look at the item above it without moving the stack pointer as well, right?
That is correct, because I don't want to move the stack pointer, because
Right.
remember, if you move the stack pointer, the gremlins will get to
Right.
the stuff that you have just uncovered.
Right.
Yep. Yep. Okay. So I hope this picture shows you why we have to do the 1 plus to get back to the address of P first. All right. So that seems correct. And I look at this line here and go like, why am I dereferencing? Because I'm not supposed to be pushing what is P first. I'm supposed to be pushing the address of P first. So this line is not needed. Okay. So I'm going to have to say delete this. Okay. And commenting out is fine, okay? And because you guys are going to use a paper test, so you just have to strike out and just say, this line is not needed. should not be there. We don't need to dereference because we're supposed to be pushing the address. But we have one more thing that we need to do because right now I'll be pushing the offset from where the stack pointer points to P first. I'll be copying the offset. I'll be pushing the offset. What am I supposed to be pushing again? I'm supposed to be pushing the address, right? So how do I get from the offset to the address? This is an item that is supposed to live on the stack. Okay, let's go back to the picture.
The address is now on the stack, the N1.
Okay, so let's get back to the picture here. Okay, this is where the stack pointer points to right now at this point. Okay, and I already put 1, which is the number of bytes between where the stack pointer points to and the thing that I need to take an address of. That's 1, right? Because literally it's just 1 byte away from where the stack pointer points to. But if I don't do any changes, I'll be pushing 1 on the stack. Is 1 the address of P first?
No.
It is just an offset from where the stack pointer points to. So how do I get to the actual address of P first?
Dereferencing.
No.
Add to the register.
Add
The offset to D.
add D to the offset.
It is the offset, yeah.
Yeah. So I need to add the stack pointer to the offset to get to the actual address.
Oh, you're trying to get that. You're trying to move it back.
Yep. So that means in the code here, I have to insert the following, which is add AD. Is that okay?
Right, because A has that already 1 offset, correct?
A has 1 in it. D is the actual stack pointer at this point.
Mm-hmm.
So when you add the stack pointer to the offset from where the stack pointer points to, you get the address. And then we just push it on the stack using decrement D and then STDA. So that would actually push the address of P first on the stack. Yep.
Why not add DA? I thought
because if you do an add DA, it changes the stack pointer, which is not.
We're not trying to do that.
We're not trying to do that. We are just trying to find out what is the address. So if you do an add DA, it would actually increase the stack pointer, which exposes portions of the stack that you don't want to expose to the gremlins.
Right. So we're not trying to move the stack pointer in this case. We're trying to move.
We're trying to find out where something is that's already on the stack.
Okay.
Okay. All right. So now we have to push the return address. So in class, I typically reverse these 2 instructions. And when I do reverse the instructions, this becomes .5 plus. But .6 plus is actually correct in this case because you can do the counting. The dot is the address of the LDI instruction. So we have offset 0, offset 1, offset 2, offset 3, 4, 5. This is offset 6. And it really is the correct return address. The address of line 254 is the correct address to push on the stack. So there's actually nothing wrong with the way that I pushed the return address on the stack. And obviously the JMP I to F is important. And then we have 2 increment D to deallocate the arguments that are still sitting on the stack. So I think that call is now fully fixed. This is the second call. And you look at the second call, I go like, let's try to use another way to do this. So I copy register D to register C. This is copy register. And the way I push N2, the address of N2 on the stack, is the same as before. So that's okay, because N2 as a label really is the address of N2 as a global variable. So I got that part done correctly. But this time, the way I compute the address of P first is to utilize register C. And register C is a copy of register D, but the copying was done before I decrement D. So that means this time I really do not need the 1 plus because I made a copy of the stack pointer before I decrement the stack pointer. So register C is the correct place to add to the displacement, to add to the offset. So that means this code here is actually 100% correct. So I compute the address of first, push it on the stack, And then we also push the return address on the stack. So let me just double check. LDIA with .6 plus, decrement D, STDA, looks good to me. JMPF, we continue execution at the subroutine, double increment D to deallocate the arguments. All right, this is the third call to the same thing. So this time, I pre-compute the address of P first using lines 272 and 273. So by the time I'm done with line 273, register C would have the address of P first already, just sitting around in register C. And then lines 274 all the way up to line 276 is pushing the address of N3. So that really is the first thing that I push on the stack. And then right after that, I push register C, which contains the address of P first on the stack. That's yet another way to get the same thing done. Are we okay so far with these lines from 272 to 278? So these lines are actually correct. There's no problem with this, but you can see this is yet another variation to get the same thing done. So the idea of the test is to make sure that you guys can actually follow what is in the register, compare that to what we need to do in the C code, and make sure that the assembly language code is actually doing what the C code needs to do. All right, so let's push the return address on the stack. Load the IA with .6 plus, decrement D, STDA, that looks good. Continue execution at the subroutine, undo the two arguments sitting on the stack, and then we got to the code that we visited a little bit earlier. So I think main is all done at this point. Okay. So when main is all done, we can now focus on the actual subroutine. And then oops, there we go. And then we basically do the same thing in the assembly code. We want to go to function F. And you'll just start with the label definitions. All right, so we want to take a look at what is on the stack, or what is supposed to be on the stack when function F is being called. That part we looked at already earlier. So if you kind of go back to the picture that I drew a little bit earlier, and then scroll up, we got this already. So we're looking at the call frame, which starts at the lowest location with the local variable result. Then we have the return address. Then we have the first parameter ppn, and then we have the second parameter of pn. So I want to double check to make sure the labels are all defined accordingly or defined correctly. So we'll go ahead and double check that. All right, so result is 0. That's good because it's the first thing in the call frame. It is the only local variable. LVS is result 1 plus. That's also correct because result is a pointer to something. Well, all we need to know is it is a pointer. Every pointer is only 1 byte wide. So we only have 1 byte as our local variable. So LVS being 1 is good. And then we define ppn, which is the first parameter, to be LVS 1 plus, and that's correct. This one here is accounting for the return address, which is also on the stack. So that is correct. And then the last one is PN being PPN 1 plus. That looks right to me. So these are all correct. And then structurally, I would check the code, the entry point and the exit point of the code before I even go into the middle of the function. So we are allocating for the local variable with these 2 lines. That looks good to me. And then I go all the way to the end to make sure that I'm deallocating correctly as well. And let's see. Yep, so I got that code here to do the deallocation. And then we have the usual LDBD, increment D, JMPB. So I got the entry point correctly done. I got the exit point correctly done as well. So now we can get into the actual subroutine to figure out whether the statements are implemented correctly or not. So I now get back to the actual code. All right. So that's going to be this line. Okay, this is the conditional statement. We want to see if ppn is pointing to a null value, or if it is not pointing to a null value, then we use that value as a pointer to get to a structure, and then we check whether the member value of that structure is greater than the value member of the structure that Pn is pointing to. Okay, that sounds like a lot. Okay, so what you can do is to say, okay, with any type of logical or logical AND operation, you have to do it from left to right. So that means the initial code here is basically checking whether ppn is pointing to a null value. So now we look at the so line 142 has the offset, line 43 has the address, line 44 has whatever ppn is pointing to, and then we check whether we push it through the ALU to see whether it's 0 or not. If it is 0, we go to else. That doesn't sound right to me, because the original C code says if ppn points to a null value, then it meets the requirement of the then statement. So we should be branching to then and not to else. But otherwise, these statements here, they're all correct. Offset, address, the actual parameter. Ooh, okay, I missed one thing. I missed one dereference, because by the time we get to line 44, by the time line 44 is done, we have the parameter itself sitting in register A, but not what it points to. What I want to compare is what it points to. So that means I need to add, oops, okay, add the following, which is another LDAA. Because otherwise I'll be comparing ppn itself to 0 and not comparing what it points to 0. So I do need one extra LDAA, and then this here also needs to be changed. Okay, so we say changed. Okay, so what we need to change it to is f underscore then, because when ppn points to a null value, that means the disjunction is true, and we just want to continue with this block of code. Are we good so far with this particular bug that I caught? The logic is reversed. Okay. What if we don't take the JNZ, the JZI, which means what it points to is non-null? Well, if it's non-null, then we can try to do the rest over here. So the rest over there is I first get the offset from the beginning of a struct node to the member value. I put it into register B, and then I add register B to register A. So the question is, what is now in register A after line 151? So remember, you have to track what is in the register. Register A before line 151 contains the address of a structure. How do we know? How do we know register A is supposed to contain the address of a structure? So this is where you have to you have to correlate the C code with the assembly code as we track down what is in register A. So A has offset to ppn. A is now the address of ppn. A is ppn, and now A is whatever ppn points to. Okay, but what exactly is ppn pointing to? ppn is, by its name, it's already telling you what it is. Okay, it is a pointer to a struct node. So if you dereference ppn once, what do you get?
A pointer.
A pointer to a struct node, right? Which is also kind of saying that whatever value is being stored is the address of a struct node. So that means at this point, we also know that A is the address of a struct node. Is that okay? So this is why it is super useful later on, because now we are adding the offset of a specific member of a struct node to the address of a struct node. So what do we end up with at this point in register A? Let me say that one more time. Register A had the address of a struct node, which means Register A is the address of the first byte of a struct node. Register B has the offset from the beginning of a struct node to a member of that structure. Once I add these two, what do I end up with?
The next value.
Mm, well, we get the address of the member, in this case, value. So at this point, A is the address of whatever ppn points to, and we are looking at the member value of that thing. So this is what it has in register A at this point. Are we still doing okay so far with this? Okay, so I can see some squinting. Um, so I'm going to kind of pause on the tracking piece here, and I want to kind of go back and focus on what are the main concepts here. What do you need to know in order to do all this tracking? Now you might be saying, but Tech, you wrote this program. Of course, you know what each register has at any point of this program. Well, the answer is I really don't. I really cannot remember my own code. Like a few hours later, I cannot remember exactly my code. I have to reason out everything as I talk to you. So none of this is really script, okay? Because I just lack the memory to do all that. So what are the concepts here? The concepts here, the first one is, as I said, would be structure. The second one is pointer. So what is a pointer? What is a pointer to a pointer? What is a pointer to a pointer to a structure? So those are the concepts that we are trying to figure out here, and and figure out how to use assembly code to do the same thing. So if I may ask, you don't have to answer, but it will definitely help with the entire class if you do at least give me some ideas. Is where are we getting lost? Because I would assume that some of us are not following what is in the register, or in this case, in what is in register A. So where are we getting lost?
I mean, it's a lot of things like this, the pattern of when things get deallocated, where things live on the stack, what's on the stack, what's not on the stack. Like there's a lot of things. It's like hard to follow exactly where
Okay.
you're going with the program. Just like as you're doing it. If I sit down for an hour and look at it, okay, maybe I'll get it. But like just following on the fly, I'm like, I don't know what's an A anymore. You know.
I see. Well, that's why we need to comment. That's why when you're tracking this code here, you need to kind of jot down notes about what is in register A, and if I cannot give you the answer like this if I don't comment. Okay, that's the bottom line. Is commenting is important, because once you do the commenting, you're only working with one small step at a time, because your mind doesn't have to track everything from the beginning all the way to the instruction that you're dealing with. Yeah, go ahead. You were trying to
I
say
think
something.
it's just hard to visualize the stack and then like trying. I think I'm just having a hard time keeping up.
Okay.
I think it's just like
Pictures help.
yeah. Like I think trying to keep track of the stack, but then
Mm-hmm.
it's just just a lot. I can't keep up and I just get lost.
I see. So I'm going to stretch the argument to say that it might also have to do with the familiarization um, with the notation that I use here. So um, so okay, are we okay with? Okay, let me scroll back up one line because I want to start from the beginning. All right. So is that line okay? With the comment of line 142. Is that okay? Because that's what the label is trying to represent. It's really just saying that, okay, in order to find ppn, the label fppn is going to give you the offset from where the stack pointer points to after the allocation of the local variables. Is that okay? So the label is representing the number of bytes between ppn and where the stack pointer points to. Is that part okay?
Yeah.
Okay.
Trying to remember what FPPN.
Hmm?
Trying to go back and see. Remember what FPPN is. That's the.
You're looking at the C code, which is on line 40. So the split screen. If you look at the top part, that's what PPN is. PPN is just one of the parameters. But we already established the labels, that are defining the offset to the parameters and also the local variables. Those were all defined correctly. We already checked that. So at this point, you can just go like, yes, I'm going to assume the label is giving us the number of bytes between what that thing is. It can be a parameter, it can be a local variable. But what we know is how many bytes it is away from where the stack pointer points to. Because we don't really care about where the stack pointer is, because the stack pointer can be here, can be here, can be here, because it all depends on, before we call this subroutine, how many other things are being called. How did we get here? So we don't really care about where the stack pointer is. We only care about where the offset is relative to where the stack pointer is pointing to. So if we're okay with 142, 143 is just adding the stack pointer to the offset of something, in this case ppn, from where the stack pointer is pointing to. So that would give us the address of ppn. Does that make sense? All right. But that's just the address of ppn. Every time we do a dereference, we turn the address into the content that the address is containing, or what is at that location. So when you dereference the address of ppn, you get ppn. So there's an intermediate step here if you wish. I can always put in that intermediate step, which is basically saying if you dereference the address of ppn, you get ppn, the value of ppn. Does that make sense? Because this part here, okay, the comment has nothing to do with assembly language programming. That really is a concept of C programming. If you dereference an address, you get the content of that address. So the asterisk and the ampersand, in a way, they cancel out each other. So are we good so far with line 144? All right. Okay. So if I do one more dereference, what do I get? I get whatever ppn itself as a parameter is pointing to. So is that okay? Is everybody connecting line 44 to line 46? So this is the important part, because what exactly is in register A at this point? We know, mechanically speaking, it is whatever ppn is pointing to. But what is the type associated with register A at this point? So if you want to work that out, then we can say ppn is a pointer to a pointer of a struct node. Okay, is a struct node pointer to a pointer. That's the C notation of a pointer to a pointer to a struct node. So that makes whatever ppn points to is a pointer to a struct node. Okay, so I want to make sure that everybody is okay with line 146 and 147, just 2 lines of comment. But these 2 lines of comment is telling you how you can track the type of the value in a register as we get along with this code. Is that part okay? ppn itself is a pointer to a struct node. How do we know it? Well, the C code says so. Okay, the C code on line 40 is saying that ppn is a pointer to a struct node. Okay, so that is given to us. Okay, that's not something that we have to figure out. So what we do need to figure out is, what if you dereference ppn once? Well, if originally it is an address to something, and you dereference it once, then it just becomes the address of the struct node. Is that okay? So mentally, if you want to use an analogy, you can think of address. Well, I mean, the holiday is coming up, so some of us will be sending cards to other people, right? So we'll be dealing with addresses. So what it turns out is, most of the time we have the address of a house. Okay, you can equate a house as a struct node. Okay, it is something that contains content that's actually cool and useful. Okay, people live in it. Is that okay? But you can also have an address of an address. In other words, you can basically have an address of where to find another address. So you can basically have an address of a PO box. You open up that PO box, you have another envelope which has another address. You find another PO box, right? So that's kind of the concept of an address of an address. Is that okay? So what PPN has is the is a specification of another PO box in which you will find another address, but this time it will be the address of a house. You know those spy movies, where there are so many different steps to find the actual suitcase, right? Each step along the way is a pointer. I'm not sure whether that analogy is working or not. Is that okay?
It's getting.
It's getting there. Okay.
I'm gonna have to.
Yeah, you actually have to.
Do it again later.
Yeah, you have to. There's no quick and easy way around. Just really spending enough time to think about what is in a register. Drawing pictures help, okay, but boiling everything down to what are the actual real issues here is also helpful. All right. So if we know that A is the address of a struct node, then by the time we get here, um, we know that instead of the address of a struct node, after we add the offset from the beginning of a struct node to one of its members to the address of a struct node, we end up with the address of the member. Okay, so does that make sense to you? So we have something that is relative to something else. So we have the address of a member of a structure being relative to the address of the structure itself. And how many bytes away is the member from the beginning of the structure? In this case, that's what the label node value is trying to represent. It's the number of bytes from the beginning of a struct node to the member that we call value within a struct node. So once we figure out the address of the struct node itself, which is in register A, and we add the offset to a specific member to the address of a struct node, we end up with the address of the member inside the structure. Are we doing okay so far with this? All right. So moving on. So this instruction here is basically doing a dereference, and and after we do a dereference, it would have become okay. So if I want to be complete, then we'll be basically doing something like this, which just basically end up with the actual value of the member. Does that make sense? Because before we had the address of the member, now we just have the value of the member. So that's the other concept, right? There are really only like 2 or 3 main concepts here. One is how do we find our parameters and local variables? 2 is how do we get the value of a local variable or a parameter? 3 is how do we access um, a member of a structure? So those are the 3 main concepts here. We are just kind of, all we are doing here is just kind of toss those concepts around in different, orders and make sure that we know how to track, what is in the register. All right. So I'm okay. So we are now getting. So now we have the entire left-hand side of the greater than. It's time to move on to the other side, the right-hand side of the greater than. So we fixed one bug, which is here. The conditional branch has to be branching to the then portion, but then the other part seems to be correct. So now we have, once again, B is offset to PN. B is the address of PN, and now B is PN. Okay. And now we have the offset to member value, and then we have B is now the address of Pn points to value, and then one more dereference, B is now Pn points to value. And now we do the compare. All right. Do we have any questions? Because this one is kind of the same thing, except it's simpler because Pn itself is already containing the address of a structure, so we don't need to do the extra dereference in this case. Is that okay? All right. So now we get to the compare. We are now doing a subtraction. So personally, I would actually write down what we are subtracting from what. So we are actually doing this. The subtraction is using register B, which is the value member of the structure the Pn is pointing to, and we're subtracting A from it. And we know earlier that A is this thing here. And then it's doing a JLI to then. Okay, so does that make sense to you? Well, look at the C code. Okay, if you look at the C code, when should we end up with the then branch? It is when register A is greater than register B. Okay, so if register A is greater than register B, then that means this branch here doesn't look right to me. Okay, and also JLI is also the wrong conditional branch to use. So we'll first take a look at whether I flip the then versus the else or not. When we perform this subtraction, the JL is basically saying we go to the then if Pn value is less than Ppn value. Okay? You look at the C code, you go like, that looks right to me. Okay, because the C code says if Pn points to value is less than star Ppn points to value, we want to end up at the then branch. And we look at the registers. Register B contains Pn points to value. Register A has star Ppn points to value. So register B being less than register A. Okay, I need to figure this out a little bit. Okay, so Pn points to value is in register B. If it is less than register A, yep, so I think that's the right direction. The label of the branching is correct. JLI is the right idea, but it's the wrong instruction to use. So what instruction should I use instead? And why do you think this L here is a problem? Why do you think that is the case? What is the type of value as a member? Okay, so let's take a look. Okay, so we want to go back to look at the definition of struct node. So what is the type of value as a member of struct node?
8-bit unsigned integer.
Is 8-bit unsigned. Okay, the key here is unsigned. So if we're comparing unsigned value and see if the minuend is less than the subtrahend, which flag should I look at? This is going all the way to, this is going all the way to going all the way back to binary comparison. Go ahead.
Sign flag.
The sign flag? Nope.
It's unsigned.
Overflow.
I mean, if it's an unsigned value, why would you use a sign flag, right?
The carry flag.
Hmm?
The carry flag.
The carry flag, exactly, which is also the borrow flag.
Right.
So we want a J what I? JCI. That's right. Okay. So let me go back to line 40 here. And this is going to be a JCI. And I forgot to comment. Okay. Changed the following from JLI to JCI. Okay. And otherwise, things are good. Okay. JCI being when B, which is Pn points to value, is less than register A, which is star Ppn points to value. We go to the then branch, so we now know the condition, the polarity of the condition, the condition of the conditional statement is correct. All right, so here's F then, okay, which is starting with line 46 in the C code. Okay, so what do you guys want to do? I don't really have a specific lab for you guys to do. So should I continue to use the lab time to explain the rest of this, or do you think
Yeah,
all good?
yeah, you can.
It's all getting recorded too? Okay, so if you're getting a little tired, it's okay. Okay, so don't push yourself to write down everything because whatever I say, whatever I write here is recorded. What you do want to record would be your own thoughts of, oh, okay, so this is how this is done. All right. All right, so we are now implementing line 46 in the C code in assembly. And once again, the assembly code gives you a hint of what we are trying to implement. So line 167 is basically hinting you that the following lines are trying to implement that specific line in C code. So it's a pattern, okay? So right now you can probably see that, oh, it looks like it's the same thing over and over again, because it is, okay? So we basically want to comment and figure out what is in the register each and every step, okay? Because if I don't do that, I cannot track down what is wrong with the code, okay? So now I can say A is offset to ppn, A is the address of ppn, A is ppn. And now I move on to B. And by the time I utilize register A, and register is not even utilized later on, okay? So I think we have a problem here. But I'll go ahead and continue to track what is in register B. So register B is offset to PN. B is PN. B is whatever PN is pointing to. Oh, I take it back. This is the address of PN. B is PN. And now B is the address of PN points to PNext, like so. And I think we're missing quite a few things, don't you think? Because the next line, line 176 is the beginning of the next statement in C. So I think I missed quite a few things. One is it's an assignment operation that has to be a store somewhere, an ST somewhere, and that's missing entirely. Okay, so that means I need to insert an ST instruction somewhere. Add this. Okay, ST something from something. So at this point, I don't know what I'm missing, which one I should be using, but from what the code is implying, I think register B is supposed to be inside the parentheses, because register B is the address of PN points to PNext, which is, that makes sense, okay? But that means, whatever is the second operand of the ST instruction should be whatever PPN itself is pointing to. So when you look at PPN, we got as far as PPN itself, but not what it points to. So what do you think I need to do here?
You have to load PP into A. So LDI A with PPN.
No. LD only works with registers.
I thought LDI.
No, you don't want to. You don't want to do LDI, because if we already are getting PPN, how do I get to what PPN is pointing to?
Do it again. Store.
Exactly. Do it again. Do the LDAA instruction again to be more specific. So this is what we need. So I'm going to say add the following, which is LDAA.
Oh, okay.
Because once we get that, then A is whatever PPN is pointing to, which does correspond to what the C code wants on the right-hand side.
Okay.
So at this point, I can now go back to here and say, that's what I need. Is that okay?
Mm-hmm.
So this is why I said earlier, it is important to track what is in the register at every single point of time, because otherwise, if I don't do this, if I don't write down the comment, I would not be able to fix the error or to spot that I'm missing something. Okay. All right, so this is the next one, and we're going to do the same thing. Okay, so Once again, offset to Pn. Address A is the address of Pn. A is Pn. So that's the right hand side. And now we have B being offset to ppn. Now, the other way to specify offset to ppn, you can also look at this as the address of ppn minus whatever the stack pointer has. That's basically the other way to document the same thing. In a way, this is a better way to specify it because it makes it really easy to look at this thing here and basically say, oh, so this is basically the address of ppn minus d, because that's what in B originally, and then we add d back to it. So using algebra, we can now say, oh, we are now just talking about ppn, the address of ppn. So that's an alternative way to document that something is an offset from where the stack pointer points to that thing. Is that okay? All right. And so now we are storing whatever pn has to whatever ppn is pointing to, or whatever is the address of ppn. That doesn't sound right to me, because register B only got as far as the address of the parameter. According to the C code here, I'm not supposed to change the parameter. I'm supposed to change what the parameter is pointing to. So I'm missing one dereference in this case. So I need to say add the following, which is a LDBB, because now B is actually ppn. So now we are saying whatever ppn has, but the reference is whatever pn has. Because register A on line 183 ends up with the value of the parameter pn. Are we still doing okay so far? So I know the code looks long, but you can see that there is a very definite pattern to the whole thing. So once you understand the pattern, it's not going to be very time consuming because you already know what pattern you're expecting. And then you look at the code and go like, well, am I getting what I'm expecting to get? So moving on to line 189. So from here on, I'm just going to say this is the address of ppn minus d. And now A is, now you don't have to do this, okay? I'm just doing this so that it is really spelled out what is in register A and why that is in register A at this point. And now this is A is just whatever ppn really is. And then at this point, B is the address of result minus the stack pointer. And now B is, okay, fine, I'll just be a little bit more concise this time. What do you think here? I mean, the next line 195 is indicating that we are now at the end of the then branch. So what do you think is wrong with this code? I mean, up to this point, everything looks right, okay? We got the right-hand side, we got the address of the left-hand side, and then we forgot to do one thing. What is it?
Store it.
To store it, exactly, because this is an assignment operation, and when you have an assignment operation, you're supposed to change the left-hand side, which can only be done using an ST instruction. So now we are missing the ST instruction. Register B has the right thing already because we're supposed to change the local variable result. So starting with the address of result is good. Register A already has the right hand side. So that's basically what we're missing. So I just have to say add the following. And we're done with this. Is that okay? So when you are working on this on paper, you can use all kinds of notation to say that I want to insert this code into this between these two lines. You can just use an arrow, okay, of your code, going between the two lines where the code is supposed to go. That would be fine. As long as I can read it and understand that you're trying to insert something, it's going to be fine. All right, so we are now moving on to the else branch, which is the recursive call. All right, so with any type of function call, okay, whether it's recursive or not does not make a difference, okay? So you just have to remember, don't try to overthink that this is a recursive call, there has to be some special consideration. The answer is no, there's no special consideration, even though it's recursive. All right, so we have to push Pn on the stack first. So once again, it is the same pattern, okay? So register A has the offset to Pn. I just added the stack pointer to it. So now A is the address of Pn. A is now Pn, and we push it on the stack. Okay, sounds right to me. And now we need to access the address of member P next of the structure that is pointed to by a pointer, which in return is pointed to by ppn. That was a long phrase, yes. Okay, but that's basically what it is. So now we have to basically do this step by step. Okay, figure out what is in register A in this case. Now, the question is that correct? Okay, I'm just asking you. Is that really where where ppn is minus whatever the stack pointer is at this point? The answer is no, because we have line 205 as an additional decrement D. So everything is off by 1 byte. So that means I need to change this. Okay, change the following to have a 1 plus, because I need to add 1 to the label because of the extra decrement on line 205. So the distance between where the stack pointer points to and where I would find ppn is now increased by 1. So you have to be very careful also to track the stack pointer to see whether the stack pointer has been changed since we allocate for all the local variables. All right, so now we can say register A is indeed the address of ppn, and then register A is ppn at this point. And ppn itself is a pointer to a struct node. So let me figure out what I'm doing with, so register B is offset to member P next. So it only makes sense for me to add register B to the address of a struct node. The question is does register A have the address of a struct node? How do we know? How can we figure that out? Well, what is in register A? Okay, according to my own comment on line 210, register A is ppn itself. So when you look at the type of ppn in the C code, what is the type of ppn? Remember, I named the I named the parameter based on its own type. So ppn has a type of a pointer to a pointer of a struct node, right? Which means it is not a pointer to a struct node. Okay, I know that sounds kind of confusing. Let me say that one more time. ppn is a pointer to a struct node, which automatically means ppn is not the address of a struct node. Is that okay? And so the way I use register A on line 212 suggests that I might be missing something. What am I missing? What ppn points to is a struct node. Is the address of a struct node, I should say, is a pointer to a struct node. So what am I missing here? We're trying to track down, okay? We're trying to track down, what is in register A at this point. I want register A to contain the address of the member P next of the structure that in return is pointed to by a pointer, and that pointer in return is pointed to by ppn. I got ppn in register A at this point, so how do I get to what I need? Remember that picture? Yes, go ahead.
You have to add one more LDA.
Yep, I need one more dereference. So this is where the picture is really useful, because what I got in register A is just ppn. ppn does not point to a struct node. ppn points to something that in return points to a struct node. Okay, so it doesn't make sense for me to add the offset of a member from the beginning of a struct node directly to, this thing, this address over here, because this address, what is in this location, is not a struct node. That is a pointer to a struct node. So I need to use one more LDAA. So register A has this address, which means register A is pointing to this location at this point. But if I do one more dereference, then register A will be pointing here, in which case it would make sense to add the offset from the beginning of the structure to member value in order to get to the address of value. So I'm missing one LDAA in the code. So I'm gonna write down here, okay, add the following line, LDAA. So now A is whatever ppm points to, and I have to comment also to say that A is a pointer to a scrub node. That is important because in order for add AB to work here, I need to make sure that A starts with the address of a struct node. So over here, A becomes the address of this thing here, which is exactly what I need in the C code. Then I need to push it on the stack. Oh, okay, but this load LDAA is not needed because according to the C code, I need to push the address of that thing, not the actual pnext onto the stack. So this has to be deleted. Okay, so I need to comment this out. Okay, delete this. There we go. And then we push that on the stack. And then we push the return address on the stack. We do the call, come back, we deallocate the arguments, and that's it. I think I forgot to check one thing, which is at the end of the then branch, I need to go around the else branch. I did not check that. So let me check that first. So, aha, I forgot about that. Because at the end of the then branch, you need to go around the entire else branch. So I need to find the label name to branch 2. It's probably end if. F end if is where I need to go. So this has to go to f underscore end if. Okay, and I need to indicate add the following line. There we go. And f end if is here. We are just copying the value of result to register A because that's what we're supposed to return according to the C code. And then we deallocate the local variables, and then we return to the caller. And I think that's it. All right. So, any questions about this entire thing? I will send you, this marked up file so that you have a copy of that too. But just having this file is not going to be very helpful because what you need to do is to make sure that you can do what I just did during the exam. And the exam is 2 hours. It's not 80 minutes. It is a 2 hour thing. So we do have slightly more time compared to exam 1 or 2. All right. So go ahead. I mean, if you guys have any questions, this would be a good time to ask. Okay, first of all, let me ask this question. Do you think going over this code is going to be helpful with what you need to turn in on Wednesday? Because I'm postponing the assignment that was originally due today to Wednesday. Do you see any resemblance between this program and the code that you need to write? Okay, so that's good. Okay, because as you write that code, try to use these techniques. Okay, try to figure out and comment what is in the register, and try to draw a picture if you want to kind of help you visualize how what things are pointing to what else. So that's one thing. Um, Next thing is, how do you prepare for the exam? I'm pretty sure that's a valid question. So what would be your answer? I mean, how do you think you want to prepare for the exam?
We have to review some things are definitely repetitive. Um,
But you don't want to just make it a repetitive thing because what I'll be testing is whether you understand the concept or not, right? So what you need to do is to look at the concept behind the repetitive pattern.
Yeah, but I mean, in terms of things that you're going to use in one program, you can use the same thing in another program.
Yes.
So if you have if you know how to like add local variables in one program, you can use that same knowledge to add local variables in another program in a different way.
More or less. Okay, so I do want to point out here because before anyone starts to memorize this entire thing, I do want to point out that the three calls in main. Okay, let me go back to the C code as well. So the way I implement line 61, 62, and line 63, they're all different, but they all got the same thing done. So you don't want to, okay, in neural net term, you don't want to overlearn. Being, you only know this very specific pattern, but you don't necessarily know that, oh, there are other ways to get the same thing done. So it's the concept behind the pattern that is important. The pattern itself is helpful because for the most part, we see the same pattern over and over again. But if I have another way to do exactly the same thing as what the pattern is doing, then you have to ask the question of, well, would I be able to recognize that this pattern here that Tech never used in his class is actually doing the same thing that we went through in this class? That would be the question because that's going to be the most important part is can you figure it out in the exam? So once again, there are only a few concepts. Okay, there's the stack, there's the call frame, how we access things in the call frame using the labels. Okay, and then we have pointers, and then we have structures. And how do we access things inside the structure? So those are I mean, everything in this particular test, the one that you're looking at right now, is really just combinations and recombinations of the same stuff. I just kind of like sometimes I remove an instruction in order to make the program not work. Sometimes I add one additional thing that is not needed, that's not supposed to be there. Sometimes I change the flag of a branch to use the wrong flag. Other times I use the wrong label to branch to. So it's really just all of those things. But in a program, if I don't tell you ahead of time and I'm not showing you which one is at fault, the question is, can you identify, what you're supposed to do at a certain point, and compare that to what the code is actually doing? If they're the same, we're good. If they're different, then you have to fix it. Is that okay? So the good thing is, none of you, I don't think, has photographic memory. That's actually a good thing because if you do, then you cannot go through the exercise again without looking at the answer. So that's one thing I want you to do. I will send you this file, okay, so you can use it for reference. But what I think might be helpful is for you to go to the announcement, download the test as it was, okay, before I added any comment, before I fixed anything, and go through that yourself and see if you can identify the problems that I identified today in this code. I mean, there might come a point you go like, okay, I'm giving up, I have no idea what's going on. Then you can refer back to what I'm going to send to you, which is the file that we're looking at this point. So I think that would be helpful. Um, oh, right. I also have office hours. So I have office hours every day, including the final week. So that means, if you're studying, you're trying to do all this stuff here, and you're running into a problem, you're running into a snag, you can come to the office hour, and I'll be more than happy to kind of go over the material with you and try to identify what is important, in this particular, final exam. All right. So, any comments, any questions at this point regarding the exam from spring or the homework assignment that is now postponed to Wednesday? What are you going to bring with you in the exam? It's open book, open notes, so you can still bring anything that's either handwritten or printed prior to the test. So what are you going to bring?
Probably the labs.
The labs. Yep. You can bring whatever you think is going to help you.
Opcode.
The opcode table. The opcode table should be kind of more or less memorized, but I understand
Should be, but it's nice to have it there.
it's nice to have it. Yes. Okay, that is good. So it's nice to have it in case you need it. That's good. The processor architecture, I don't think is going to be helpful in this case. So I wouldn't put too much importance into that thing. Notes about binary comparison may still be helpful because you need to know which flag you're supposed to use, or and also the ALU itself can still be useful. Okay, because when I do an AND AA, what am I really doing? Because it actually does touch two things. It would touch the Z flag. It will also touch the sign flag. So so that part can be helpful if you have that diagram with you. You can bring this entire solved exam with you. If that's something that you think will help. I think if you go through this process and you integrate the knowledge into your mind, that would be more helpful. But if you think, just in case, okay, I want to have this as a backup so I can refer back to the solution of the exam in spring, be my guest, okay? That would be fine as well. Because when I said anything that's handwritten or printed, I really meant it. Nothing, there's no restriction whatsoever. Which also means, it's not going to be exactly the same thing. It'll be a variation of some kind. Any other questions? Any specific question about the instructions that was used in this entire thing? I mean, we are basically using the same stuff over and over, right? LDI, LD, ST, JMPI, decrement, increment, store. We are not really using a whole lot of variation of instructions. It's the sequencing of the instructions that can be tricky. All right. If there are no additional questions, I can stop the lecture and stop the recording. You good? All right. So I'm going to stop the recording, and I think the Computer Science Club is going to have a snack, thing, at 1:30.
Yes.
Okay, and I'm gonna contribute with mini cookies from Costco, and also tortilla chips and salsa, also from Costco. So if you guys want to kind of get a snack at 1:30, you'll be downstairs at the STEM home base, right? So we all good? All right. So I'm gonna stay here, okay? Because this is technically the lab time. So if you want to continue to work with your lab, you know, in the lab here, that's all good. If you want me to diagnose, if you want to get River Spider working and it's not working for some reason, I can help you diagnose with those problems too. So that's what this time is going to be used for. And if you are leaving, I'll see you on Wednesday, and then we'll talk about the solution of the homework on Wednesday, which is actually a double reinforcement of the stuff that we talk about today because they are very similar. All right, so let me stop the recorder, and then we'll go ahead and.
Is that our last class on Wednesday?
That is correct. The last